What is a photodiode? How does it function and its application? A photodiode is a semiconductor device that converts light into an electrical current. It operates based on the principle of the photoelectric effect, where light photons hitting the surface of the photodiode generate charge carriers, electrons and holes, in the semiconductor material, leading to an electric current. Photodiodes are used in a variety of applications where light detection and signal conversion are needed. The structure and functioning of a photodiode can be understood by breaking down its key components and the physical principles that allow it to operate. 1. Structure of a photodiode. A photodiode is typically made up of the following components. Semiconductor material. Photodiodes are usually made from materials like silicon, germanium, or gallium arsenide. Silicon is the most common because of its efficiency and low cost. P-N junction. The heart of the photodiode is a P-N junction, similar to that in regular diodes. This junction is where a layer of P-type semiconductor material, rich in holes or positively charged carriers, meets a layer of N-type semiconductor material, rich in electrons or negatively charged carriers. Depletion region. At the interface of the P-type and N-type materials, a region devoid of free charge carriers is formed. This region is called the depletion region. It acts as a barrier for charge flow in normal conditions, but is crucial for the detection of light. Window or lens. Some photodiodes have a transparent cover, window, or lens that allows light to enter and be focused onto the active area of the diode. Electrical contacts. Metal contacts are connected to the P-type and N-type regions, which allow for the extraction of the generated current. 2. Functioning of a photodiode. The functioning of a photodiode relies on the photoelectric effect. Here's a step-by-step breakdown. 1. Photon absorption. When light, photons, strikes the surface of the photodiode, the photons are absorbed if their energy exceeds the bandgap of the semiconductor material. The bandgap is the energy difference between the valence band, where electrons are bound, and the conduction band, where electrons are free to move. 2. Creation of electron-hole pairs. The absorbed photons transfer their energy to the electrons in the semiconductor, exciting them from the valence band to the conduction band. This process creates electron-hole pairs. An electron is a negatively charged carrier, while a hole is a positively charged carrier, the absence of an electron. 3. Separation of charges in the depletion region. The P-N junction's depletion region is crucial in separating these charge carriers. Due to the built-in electric field in the depletion region, arising from the potential difference between P-type and N-type materials, electrons are pulled towards the N-type side and holes towards the P-type side. 4. Generation of photocurrent. As the electrons and holes are separated and move towards their respective regions, electrons to the N side and holes to the P side, a current is generated. This current is proportional to the intensity of the incident light. 5. Output current. The movement of charge carriers creates a photocurrent, which flows through the external circuit. This current can then be measured or used to drive other components of an electronic system. 3. Operating modes of a photodiode. Photodiodes can be operated in 2 main modes. Photovoltaic mode, zero bias. In this mode, the photodiode operates without any external voltage applied across the P-N junction. The diode generates a voltage and current in response to light, much like a solar cell. This mode is slower but is used in applications where power consumption needs to be minimized. Photoconductive mode, reverse bias. In this mode, a reverse voltage is applied across the diode. The N side is connected to a positive voltage, and the P side to a negative voltage. The reverse bias increases the width of the depletion region, making the photodiode more sensitive to light and faster in response time. However, this mode also introduces more dark current, a small leakage current even when no light is present. 4. Response time. Capacitance of the P-N junction and the size of the photodiode affect how fast it can respond to changes in light intensity. Smaller photodiodes, or those operated with reverse bias, typically have a faster response time. Speed. Faster response times are critical in applications like fiber optic communication, where high-speed detection is necessary. 5. Dark current. Dark current is the small current that flows through the photodiode even in the absence of light. It is caused by the thermal generation of electron-hole pairs and depends on the material and operating temperature. Summary. In essence, a photodiode detects light by converting incoming photons into an electrical current. The p-n junction and the depletion region play a critical role in separating charge carriers generated by the light, creating a current that is proportional to the light intensity. Depending on the mode of operation, photodiodes can be used in a variety of applications, from slow solar cells to high-speed optical communication devices. The key characteristics of a photodiode determine its performance in various applications, including its sensitivity, response speed, and noise levels. Here's a breakdown of the most important characteristics. 1. Responsivity. Definition. Responsivity is the ratio of the generated photocurrent to the incident light power. It is usually measured in amperes per watt, A/W. Dependence on wavelength. Responsivity varies with the wavelength of the incident light because the energy of photons depends on their wavelength. For example, a photodiode made of silicon is more responsive to visible light, but less so to infrared light. Optimization. Different materials are used to optimize responsivity for specific light spectra, e.g., silicon for visible light, germanium for infrared light. 2. Dark current. Definition. Dark current is the small current that flows through the photodiode even when no light is present. Cause. It is caused by the thermal generation of electron-hole pairs within the semiconductor material and increases with temperature. Impact. Dark current introduces noise into the system, reducing the accuracy of low-light measurements. Minimization. Cooling the photodiode or using materials with lower intrinsic carrier concentrations can minimize dark current. 3. Noise equivalent power, NEP. Definition. NEP is the amount of light power that produces a signal equal to the noise level of the system. It is measured in watts per square root hertz, W/square root hertz. Lower NEP. A lower NEP means the photodiode can detect weaker signals with less noise, making it more sensitive. Relation to dark current. A photodiode with lower dark current will typically have a lower NEP. 4. Quantum efficiency, QE. Definition. Quantum efficiency is the ratio of the number of charge carriers generated, electrons or holes, to the number of incident photons. It is expressed as a percentage, percent symbol. High QE. A photodiode with a high quantum efficiency converts more incident photons into electrical signals, making it more efficient. Dependence on wavelength. QE depends on the wavelength of the incident light and the material used in the photodiode. For example, silicon photodiodes may have a high QE in the visible range, but lower QE for ultraviolet or infrared light. 5. Response time and bandwidth. Response time. The time taken by the photodiode to respond to changes in light intensity. A faster response time means the photodiode can detect rapid variations in light. Factors affecting response time. Capacitance of the p-n junction. Larger junction capacitance slows the response time. Reverse bias voltage. Applying reverse bias increases the depletion region, reducing capacitance and speeding up the response. Bandwidth. The maximum frequency at which the photodiode can operate while still providing a meaningful output. A high-bandwidth photodiode can handle signals with faster modulations, e.g., fiber optic communication systems. 6. Spectral response. Definition. The range of wavelengths over which the photodiode can effectively detect light. Material dependency. The spectral response is determined by the material of the photodiode. For example, silicon, sensitive to wavelengths from 400 nanometers, ultraviolet, to about 1,100 nanometers, near-infrared. Germanium, extends into the infrared range, useful for wavelengths up to 1,700 nanometers. Filter. Sometimes photodiodes are equipped with optical filters to restrict the spectral response to a specific range, improving performance for specific applications. 7. Capacitance. Definition. The photodiode's capacitance is the ability to store charge in the depletion region. Influence on response. Higher capacitance slows down the photodiode's response, reducing the speed of detection. Reverse bias. Applying a reverse bias reduces the capacitance, improving the speed and allowing for operation at higher frequencies. 8. Linearity. Definition. Linearity refers to how well the output current of the photodiode correlates with the intensity of the incident light. High linearity. A photodiode with high linearity will generate a proportional increase in current as the light intensity increases, making it more accurate for light measurement applications. 9. Temperature sensitivity. Impact. Photodiodes are sensitive to temperature variations. As temperature increases, dark current and noise increase, which can affect the overall performance. Compensation. In some applications, cooling or temperature compensation circuits are used to stabilize performance in varying temperature conditions. 10. Reverse breakdown voltage. Definition. The reverse breakdown voltage is the maximum reverse bias that can be applied to the photodiode without causing it to enter a breakdown region, where it becomes permanently damaged. Design consideration. Photodiodes are often operated with a reverse bias, so knowing this limit is important to avoid damage during operation. 11. Size of active area. Definition. The active area is the region of the photodiode that is sensitive to light. Larger active areas can collect more light, producing a stronger signal. Trade-offs. Larger active areas tend to have higher capacitance, which can slow down the response time. Conversely, smaller active areas are faster but may collect less light. Summary of key characteristics. Characteristic explanation. Responsivity measures the efficiency of converting light into current, A/W. Dark current, the small current that flows even in the absence of light. NEP, minimum light power detectable, limited by noise, W/Hertz. Quantum efficiency, QE, percentage of photons converted to charge carriers. Response time, how quickly the photodiode responds to changing light intensities. Spectral response, the range of wavelengths the photodiode can detect. Capacitance affects the speed of the photodiode. Higher capacitance leads to slower response times. Linearity describes how well the output current follows the light intensity. Temperature sensitivity, impact of temperature on dark current and performance. Reverse breakdown voltage, maximum reverse bias before damaging the device. Active area, the portion of the photodiode that receives light. Larger areas capture more light but are slower. Understanding these characteristics is crucial for selecting the right photodiode for specific applications, balancing sensitivity, speed, and efficiency. Photodiodes are used in a wide variety of applications across different fields because of their ability to convert light into electrical signals. Here are some of the major applications of photodiodes. 1. Optical communication systems. Fiber optic communication. Photodiodes are essential in fiber optic communication systems, where they are used to detect light signals transmitted through optical fibers and convert them into electrical signals. This enables high-speed, long-distance communication, such as in internet infrastructure and telecommunications. High-speed data transmission. Photodiodes with fast response times are used to detect modulated light signals in high-speed data transmission, such as gigabit Ethernet and broadband networks. 2. Light detection and measurement. Light meters. Photodiodes are used in light meters to measure light intensity for photography, environmental monitoring, and laboratory instruments. Ambient light sensors. Devices such as smartphones, tablets, and laptops use photodiodes to detect the surrounding light level and adjust the brightness of the screen automatically. Solar irradiance sensors. Photodiodes measure solar radiation intensity for applications in solar power systems, meteorology, and agricultural studies. 3. Medical applications. Pulse oximeters. Photodiodes are used in pulse oximeters to measure the oxygen saturation in a patient's blood. They detect light that passes through a patient's tissue and measure how much of it is absorbed by oxygenated versus deoxygenated blood. Biomedical instruments. Photodiodes are used in various medical diagnostic tools and instruments to detect light signals for imaging, measurement, and diagnostic purposes, such as in photoplethysmography, PPG. Medical imaging. Photodiodes are used in computed tomography, CT, scanners, and other imaging devices to detect X-ray light and convert it into electrical signals for image formation. 4. Solar energy applications. Solar cells. A solar cell is essentially a large area photodiode that converts sunlight into electricity. In solar panels, photodiodes capture light from the sun and convert it into electrical energy, which is then used to power homes, industries, or stored in batteries. Light harvesting. Specialized photodiodes are used in systems that harvest energy from ambient light for powering low-energy devices. 5. Safety and security devices. Smoke detectors. Photodiodes and photoelectric smoke detectors detect changes in light caused by smoke particles scattering the light beam. This allows the alarm to be triggered when smoke is detected. Intruder alarms. Photodiodes are used in infrared security systems where they detect the interruption of a light beam, such as from a laser or LED, that signals a breach in the monitored area. Motion sensors. In some motion detection systems, photodiodes are used to detect the infrared light emitted by objects in the environment, enabling them to sense movement. 6. Barcode scanners. Photodiodes are used in barcode readers to detect the reflected light from the black and white bars of a barcode. The differences in the reflection intensity are converted into electrical signals to decode the information in the barcode. 7. Position and proximity sensing. Proximity sensors. Photodiodes are used in devices that detect the presence or absence of objects by measuring reflected light. Commonly used in touchless switches, hand dryers, and parking sensors in vehicles. Optical encoders. In industrial machinery and robotics, optical encoders use photodiodes to detect the position or rotation of a motor shaft or mechanical component by reading light patterns from a moving disk. Laser rangefinders. Photodiodes detect the reflected light from a laser in rangefinders, allowing precise distance measurements based on the time of flight of the laser pulse. 8. Laser-based applications. Laser diode feedback. Photodiodes are used to monitor the output of laser diodes and provide feedback to maintain stable laser intensity or wavelength, such as in CD, DVD drives, and laser printers. Laser safety systems. They can detect laser beams and safety systems to ensure that dangerous laser radiation is not present in unintended areas. 9. Environmental monitoring. UV radiation measurement. Photodiodes are used to detect ultraviolet, UV light for measuring UV radiation levels in environmental monitoring systems, skincare applications, and UV sterilization processes. Pollution detection. In air pollution monitoring, photodiodes detect light scattered by particulate matter in the air, helping to quantify pollution levels. 10. Optical sensors in industrial automation. Optical switches. Photodiodes are used in optical switches to detect the presence of objects in manufacturing lines or detect product position during automated assembly. Material sorting. Photodiode-based sensors are used in industrial systems to distinguish between different materials based on how they reflect or transmit light, such as in recycling facilities. 11. Consumer electronics. Remote control receivers. Photodiodes and infrared receivers detect the infrared light emitted by a remote control, allowing the control of TVs, air conditioners, and other consumer devices. Optical disc drives. In CD to DVD drives, photodiodes detect the reflected light from the surface of a spinning disk to read and write data. 12. Scientific research. Spectrophotometers. Photodiodes are used in spectrophotometers to measure the intensity of light at specific wavelengths, useful in chemical analysis, biological research, and environmental science. Astronomy. Photodiodes detect faint light from distant celestial objects, contributing to optical and infrared telescopes for astrophysics research. 13. Counters and timers. Counting applications. Photodiodes can be used to count the number of objects passing through a light beam in automated systems, such as counting items on a production line or determining traffic flow. Summary of key applications. Application usage. Optical communication detects optical signals in fiber optic and data transmission systems. Light measurement used in light meters, ambient light sensors, and irradiance monitoring. Medical devices utilized in pulse oximeters, medical imaging, and diagnostic tools. Solar cells convert sunlight into electrical energy in solar panels. Safety and security used in smoke detectors, motion sensors, and intruder alarms. Barcode scanners reads barcodes by detecting reflected light patterns. Proximity sensing detects object presence in touchless switches and motion sensors. Laser-based systems monitors laser output in laser diodes and laser rangefinders. Environmental monitoring measures UV radiation and particulate matter for pollution detection. Industrial automation detects object presence, material sorting, and optical switching. Consumer electronics used in remote control receivers, optical disc drives, and light sensors. Scientific instruments measures light intensity in spectrophotometers and telescopes. Photodiodes are indispensable across multiple industries for tasks involving light detection, signal conversion, and energy harvesting. In summary, photodiodes are versatile devices widely used in detecting and converting light into electrical signals across various industries.